Hi everyone, I'm Mr. Ellingson and I'm going to walk you through the pre-lab discussion for the titration lab. I would love if you were able to come in today and be in the classroom and do the titration lab, but that isn't the case. So let me show you what we're doing. The goal of the titration lab is to determine the concentration of an unknown base. This is NaOH, it's a base solution. We need to figure out the molarity of it. We can do that through this process of titration, which is the controlled addition of an acid to a base. We can use a acid-base indicator, phenolphthalein, and we can look for the end point, which is the color change. Phenolphthalein in an acid solution is clear and colorless, and between 8 and 10.0 pH, it changes from clear colorless to pink. So we're looking for lightest perceivable pink to stop our addition of our base to our acid. Okay, the way we're going to add acid and base together, we're going to put it into this Erlenmeyer flask right here, and we're going to use these burettes. Okay, these burettes are marked to the 100th, we're guessing at the 100th of a milliliter, from 0 to 50, from 0 to 50. So we're going to add acid to the acid burette, we'll add base to the base burette, and then I'll walk you through it. Now, at the equivalence point, pH is 7. Moles of H plus equal moles of OH minus. And because of that, we can use this equation right here. Molarity of the H plus times volume of the H plus is equal to molarity of the OH minus times volume of the OH minus. For this experiment, our molarity of H plus is 0.150 molar. Our volume of the H plus, we're going to read that off of the acid burette. Our molarity of the OH minus, that's what we're after. We're going to calculate that. Okay, so that's our question mark. And our volume of OH minus, that is going to be read off of the volume of the base burette. All right, so let me show you how this works. This is a stopcock here. It has a valve. If it's with the flow of the liquid, it's on. If it's perpendicular, it's off, okay? And so the first thing that's important before you start filling this up with acid is close the stopcock so that doesn't come leaking out of here, okay? Now, we don't know what was used in this acid burette before we got it, and so we're going to take some of our acid after the burette's closed. We're going to add a little bit of that acid, maybe 5 mils, and into it, and we're going to roll this around like this, and we're going to slowly raise this hand so that the whole inside surface gets wetted with this acid solution. Okay? And as we slowly raise this, it'll eventually just pour into the sink, and we'll be done with it. All right? And the reason you do that is if there was anything that was like water droplets in here, that would change the concentration of the acid, or if there's any dried base in here or something, that would neutralize some of the acid. So we want to just make sure that everything that's in this acid burette is exactly 0.150 molar HCl, and that's how you do it. So the next thing we're going to do is we're going to just fill up the burette to the 0 mark, which is on the top. We're going to actually go a little bit above that. And we're going to put it in this burette clamp and hold it there, okay? And what I'm going to do next is I'm going to have this little Erlenmeyer flask, which is my waste Erlenmeyer flask. I'm going to open up this stopcock, which is going to drain some of the acid out. I'm going to drop it down till it gets to 0 right here. Okay, I'm going to watch with my eye level on the mark until it gets to 0. I'm going to touch off any drop that's hanging there, and now that's what we call a loaded burette. Okay, I'm going to do the same to my base burette. Make sure the stopcock is closed. I'm going to put about 5 milliliters in there. I'm going to wet the entire inside surface, let that drip into the sink. Fill this up a little past the 0 milliliter mark with my base of unknown concentration. Get it inside, attached with the burette clamp here. Use my waste burette. I'm going to slowly drain some base out of here till I get my meniscus up on top here to the 0.00 milliliter mark. Touch off the drop. Okay? This will be done for you in the virtual lab that you're going to be doing. So they'll start you out with your acid and your base. You'll be able to see it very clearly at the 0 mark. Now with my larger Erlenmeyer flask, I'm going to add a couple of drops of phenolphthalein to it. If you don't do that, you're not going to see the color change. I'm going to add some acid to it. Okay, that is 15.00 milliliters of acid. If I want to add a little water to this, that's fine. I can add a little water to it. It's not going to change anything because I haven't changed the moles of acid in here yet by adding water. The total number of moles of H plus are still there. Okay, it just gives me a little more volume so that I have a little more to look at and observe. Now I'm going to add base to this. And when I add base, I'm swirling the entire time. And what you'll notice is it'll start to turn pink, and then that pink will go away. And as you add more, it'll stay pink longer. You're getting close to the end point at that point, okay? And what you're after is hitting the exact lightest perceivable pink. And with swirling, it has to stay a minute. And it's very helpful to have like a white background so you can see if that's pink or not. So I don't know if you can see that, but that's definitely pink. We want lightest perceivable pink, and this is way, way pink. And so what we did was overshot our endpoint, which is not a problem because we can back titrate. Okay, that means we can add a little more acid. When you add a little more acid, you'd expect this to go clear and colorless. Okay, it did. And now we can add base at a slower rate, a much more controlled approach to the endpoint until you get a lightest perceivable pink to stay for a minute. That went away. And when you get good at this, you can kind of spin this so quickly that you can clip off about a third of a drop. Okay, and so you can see right there that is very light perceivable pink. Okay, there's definitely not clear and colorless, and it's not dark. All right, so that is the end point. Now, at the end point, we're going to measure our volumes here. Okay, so we used 16.50 milliliters. Of acid, and we used 20.15 milliliters of base. And we can just rearrange this equation now and solve for MOH minus. Okay, when I do that, I'll get my concentration of my base. So it is 0.15 times 16.50 divided by 20.150. My concentration of base, that is M, is 0.123 molar. Okay, get out of the way so you can see that. That's what you're going to be doing virtually in our pivot lab. Okay. All right. So that was the how to do a titration if you were actually did hands-on titration. Here's a picture that I took out the window of the chemistry lab here. Had better light. That's kind of lightest perceivable pink. And what I would do when you're doing the titration is I would record the volume of base added to get that lightest perceivable pink, write it down, and then add a little bit more acid to it to back titrate. Swirl that for a minute, and if the pink goes away, that number that you have written down is you nailed it. If it gets lighter, then cross that number out and record the new one because that's even lighter perceivable pink. Okay, you want the lightest possible perceivable pink that stays after for a full minute of swirling. All right, so the other thing I want to do is I want to talk about error analysis, and this experiment is a neutralization. Acid base yields water and a salt, and let's just say that you know the rest of this here. We're trying to figure out the molarity of the base solution. We start with 15 mils of 0.100 molar HCl, and we hit the end point, lightest perceivable pink. I'm going to set up 5 situations for you. I want you to make a decision as to what error occurred, if an error occurred, and if it did occur, what is the error? And then how did the error affect a direct measurement, and how did that incorrect measurement affect my final calculated concentration of unknown base? Okay, so here's situation number 1. They didn't rinse the burette out like I showed you in this video. It was wet, it had water droplets in it, and they just filled it up with acid and went. What I want you to do is tell me if this is an error, and tell me how the final calculated MOH minus would be affected. Okay? Pause the video, come up with an answer, and then bring this back up to play, and I'll share my thoughts with you. Okay, so taking that MH plus VH plus is equal to MOH minus VOH minus, rearranging it to solve for MOH minus, what I get is okay, so if one of these 3 measurements were changed, then your calculated MOH minus will be affected. All right, so here's the error. Those water droplets changed the molarity of the acid. They diluted the acid a little bit. You're using 0.100 molar here, thinking that's what it is, but it was changed. It was diluted a little bit inside the burette. And because of that, the error is that you had to use more acid to neutralize that amount of base. Okay? And since the volume of H plus is in the numerator, what's going to happen is your calculated MOH minus will also will calculate out too high. Okay? So the logic, once again, because you diluted the acid solution with those water droplets, you had to use more of the dilute acid. So the measurement that was changed is your VH plus, your volume of acid added. And that error, which we didn't catch, increased your calculated MOH minus. Let's try another one. Okay. So what I want you to do is think about this one, commit to some sort of answer. Is this an error? If it is, how is MOH minus calculated MOH minus affected? Go through the kind of the same process and pause the video, come up with an answer, and then start it back up, and I'll talk you through my explanation. Okay, so leaving the acid out to the environment over the weekend evaporated some of the water from the acid. That concentrated the acid solution. So the molarity of the acid is no longer what we think it is. It's actually a little bit larger. And because of that, we had to use less of it. Okay? And so how this experiment was affected was the VH plus is going to be too small. And since that's in the numerator of this equation, our calculated MOH minus will also be calculate out to be too small. All right, try this one. Kind of couch your answer the same way. Think about this equation. Which variable on the right is affected and how is that going to calculate out, change your MOH minus. Pause it, get an answer, then bring it back. Okay, this is actually not an error because we haven't changed the molarity, any number of moles of H plus, and we haven't changed any moles of OH minus. And therefore, just adding water is going to give you, like I mentioned in the demo, is going to give you a little bit more liquid to see, but it doesn't increase or decrease moles of H plus added, and it doesn't increase or decrease moles of OH minus added. This is not an error. Okay, is anybody 3 for 3 yet? See if you can go 5 for 5 here. Okay, this one actually happened a couple years ago. I made up the solutions. Okay, but anyway, pause the video, see if you can find the error, if there is one, and see if you can predict what how that error will affect your calculated MOH minus. Okay, so if the bottle is labeled 0.150, but it's actually more concentrated than that, we don't know that, but if it's more concentrated than that, we're going to actually use less of it than if it was 0.150. And because we use less of it, our volume of H plus is going to go down, okay? And because of that, if your numerator gets smaller, your calculated MOH minus will also be smaller. Okay, that's how that error will affect that calculation. All right, number 5. This group overshot their endpoint, used their data. How would this error affect their final calculated molarity? Same thing, pause the video, see if you can come up with the answer. Okay, if they overshot their endpoint and called that good, the error would be that they added too much base solution. That would mean your VOH minus is too large. Since that's in the denominator, that's going to affect your calculation, causing your molarity, calculated molarity of OH minus to be too small. All right, one last one, bonus round. Give this one a try, see what you think. Okay, this is a sig fig error, 15.0, 3 sig figs, instead of 15.004 sig figs, but it isn't affecting the any of the variables on the right. It's not affecting the 0.100 that you know, the molarity. The volume of the acid and the volume of the base are just to 3 sig figs instead of 4. All that's going to do is cause you to correctly calculate the molarity of the OH minus, but just to 3 sig figs, not 4. Okay? I hope you did all right on that. The lab today, you're going to be asked to do some error analysis, but for now, that's good. You can go to the lab at this point and give it a try. Okay? Good luck and have fun. Oh, welcome back. You stayed. I want to do some kitchen chemistry. Very quickly. Have you wondered why some recipes call for baking soda and others call for baking powder? They're both leavening agents. That means that when added to baked goods, they help them rise. They do this by causing a chemical reaction between an acid and a base, and it forms, among other things, CO2 gas. That CO2 gas, those bubbles get trapped in the dough or batter, causing the batter to rise. Okay? Baking soda is a base only. And for it to react to create CO2, there needs to be an acidic ingredient in the recipe, like buttermilk or vinegar or fruit juice or something like that. As a base alone, it won't react and form CO2. Baking powder, on the other hand, is a mixture of an acid and a base. It's all in here, so the recipe doesn't need any acidic ingredients to make the CO2. All right, let me show you what I'm talking about. This is these are 2 beakers of just water. I'm going to take and add just a little bit of food coloring to them. So hopefully you can see bubbles. And with the baking soda just being a base, you would expect to not see really any bubbles formed when it's just dissolved in water. There's no acid. Okay? And for the baking powder, you would expect to see bubbles formed because, and you can see them, haziness there is the bubbles coming up through the water, because there's acid and base together. Now I should be able to add acid to this baking soda, which is a base, and get bubbles to form. And you can see it does. Okay? So how cool is that? Aren't you glad you stayed around till the end? Have a good day, guys.